Welcome to another exciting biomedical signal processing class. I've been sitting here doing some office hours trying to see what we could do to do some digital signal processing with integers. How exciting. Isn't that exciting? Eh? Not so exciting. It's not exciting. How'd you guys make out with your little digital discrete Fourier transform without floats? Yeah?
Realized we needed float to calculate 2 pi on 2 pi on n.
Why would you need to calculate 2 pi on n?
Seems necessary.
Well, if you consider, let's consider the example of our prior class where we did a computation of a sine wave and stored the entire thing in advance in a wave table. And the wave table, in this case, is fixed audio data. So if you do the computation in advance and store the data, then in theory you shouldn't have to do things like math.sine. And if you consider that you're going to be scaling everything so that it's correlated against sine waves that are stored in wave tables, then in theory all you really need to do is have space. So what you're really doing is you're trading the computational effort of a floating point unit for space. In my view, it's pay now or pay later. So you pay up front, do all of your sine and cosine functions up front, and then you store your data so that they can be used by some kind of crippled computer, perhaps a let's say floating point challenged microcontroller, like an 8-bit toaster controller, might not actually have a floating point unit. So we get around that by creating a wave table and doing our computations in advance. So what I did in here was I said, hey, look, sine waves. What do sine waves do? Well, they're implemented by a transcendental function that we call math.sine, and it outputs a floating point number, a double precision floating point number, which ranges from -1 to +1. So what do? I say I don't want it to range from -1 to +1. I want it to range from 0 to 1. So first thing I do is I add 1. So now it's ranging from instead of -1 to +1, it ranges from 0 to +2. So that's easy enough to see, right? Because if you add 1 to something that goes from -1 to +1, gesundheit, it goes to -1 to, it goes from 0 to +2. Then divide it by 2, and now it goes from 0 to 1. That's fair. Now we said, gee, I wanted to take the bandwidth of a signed byte, and signed bytes range from -128 to +127. That's what signed bytes do in Java. So then what I said was, okay, great, we'll multiply it by 255. So now it's going to range from 0 to 255, but as a floating point number. And then I'll subtract off 128, and now it's going to range from -128 to +127. And that is going to be set equal to a floating point number t. And I said, groovy. That's just what I want. And what I'd like to do is I'll store it now in my little wave table, which I will call fixed audio data, and then I'll add 1 to the little increment. And so then when I do this computation in advance, I should be able to print out all of my little deltas and then proceed to show how you can back out the original floating point number if you want it. And then I will show what the original sign looks like versus the byte versus the floating point. And then for the delta, I want to see what the error is between the now scaled and quantized sine wave versus the original. But I also want to, at the end of the day, print this little wave table. And I'd like to show what those numbers are and maybe set up something so that I can use that digitized version of the sine wave for my correlation later on. And so what I'll do here is I'll just sort of run it and show you, and then I'll describe what's going on here at the bottom. The sine wave starts at 0. At 90 degrees, it's about halfway through its positive excursion. Its apogee is around 120. Now remember, we needed something that goes from minus 127 to minus 128 to plus 127. So by going to 120, we're pretty close. We're getting there. So now it's peaking out at 120. It starts to decline to 74. Then it heads at 180 degrees. No, is that, yeah. Yeah, 180 degrees. It passes through the origin. Then it says minus 75, which is almost symmetric with plus 74. And then it goes minus 121, which is quite symmetric with 120. Then it goes back up to minus 75, and then it's at 0 again. Now, I can correlate with that using only integer functions, because if you recall, correlation is just an integration of a arbitrary input function against some kernel, and the kernel is just the thing you're comparing it against. And what you're doing is you're integrating over a time we'll call it a limited time sequence. So let's say from t0 to t1, we'll run our little integral of an arbitrary input function against some arbitrary compare function, and the compare function in this case will be a sine wave. So then your question is, okay, yeah, great. How do I change the frequency of the sine wave? The answer is you got to change the positions over which you do your sampling. So if you want to resample the sine wave, obviously you're going to need more than, let's say, 11 different sample points in a sine wave if you want a high precision sine wave. But I'm going to do a simple sine wave because that's better for us so we can see what's going on. Then we're going to have to advance the pointer into the wavetable more quickly in order to change our frequency. So that's kind of what I was hoping you guys would get to. Then the question is, how do I compute, what was it, 2 times pi times n or something? Divided by n? Well, if you look on over here, the computation for let's say the increment on epsilon can be done in advance, where you go to decide how big your wavetable is going to be. So now what you've got is a mechanism by which you can pre-compute everything you need. Everything you need can be pre-computed, and in theory you could take some audio data like this and print it out as an array that can initialize an arbitrary data structure. Right, and so I don't know what I have available for doing stuff like that. Print utils dot print, and now I've got some print facilities here. Print char array, print component, print numbered lines, print money, print reflection, print state. Yeah, I may not have something like that. Let's see what I have here in the mat1 library. Mat1 dot print. Doesn't look like I got anything. So I'd have to write my own function. Excuse me while my phone interrupts my class here. We'll have to do something about that. Here, put that there. This goes over there. Here. That's how I turn off the phone. There's a button or something, but I never learned how to do it. I don't have a smartphone. I have a dumb phone, but that's smart. So what I was thinking is this. What we would use is some kind of a model for printing out arrays, and then we would use that model for printing out arrays so that they can be reused in our programs. So if you think about it, when you create an array, let's create one for fun. Integer array A equals 1, 2, 3, end quote, sem. Wouldn't it be nice if you could print a Java array? so that it came out just like this. Can you see it okay? Yeah. So I thought, well, why not make that a utility? Print Java array. That would be fun, right? Do I already have such a utility? I might do. Find in path, print Java array. That just sounds like something you should be able to do. Print Java. Can't you just print Java, whole project? I want to pass in an array and have it print Java. Oh, it looks like it's already in there. System utils print Java home. That's not right. Print Java home. No, I don't have one. Why did I think I had one? I don't know. So what we'll do is we'll write our own print Java doodad, and it'll output something like this. And could probably start it off like this. Print Java, and then pass in the fixed audio data. And then what this will do is it'll create the method print Java, and we'll start by writing the spec on this, and we'll just say paste is output, and if we look by Control Q, you can see where the Java doc has been formatted. So what I would do in this case, I think, is something like this. Sout Control J enter, end quote int a equals end quote, and then I think what I would do is write a little for loop to iterate through each one of the elements and then print out the element with a comma. So probably something like this. For integer I equals 0 while I is less than fixed. Oh, maybe it shouldn't be called fixed audio data when it's in here. Why don't we just call it D? D is for data, right? So we'll make it, oh, I know. Yeah, D is for data. Well, I is less than D dot length, I plus plus, and now I've got maybe a simple print statement to do, and it's something like this. A of I, oh no, it's D of I, isn't it? Shall we call it A? A, D, A, make it A. A, yeah, for array. A is for array. A of I plus quote comma, and so that'll put in a new line, and then at the end of the day we need to close the brace with a semicolon, and now I think maybe you're ready for this. Probably needed a carriage return at the beginning, but that's not too bad. Sout Control J enter. That'll give you a carriage return at the beginning. If you want, you can use print line, and then every sort of 10 elements, if I mod 10 equals 0, print out a new line. That way it'll print it out, 10 elements in a line, and then put in a carriage return. That makes it nice. And there it is. Although the first time through it put in the carriage return, why would that be? Because if I is 0, if I is 0, I mod 10 will equal 0. Because there'll be 0 left over? Huh. Is there a better way to do this? Yes, sir.
Just arrays dot feature
where it's just called A dot toString? What happens if it goes off to the edge of the... It won't put in the carriage return every once in a while, right? Yeah, it's not a bad one. I like it, but it's not... Are those curly braces or square brackets? But I need curly braces for Java, right? The Java compiler wants curly braces. Right? In other words, if you take this, copy it, you can essentially go into an arbitrary program and just sort of paste it on in, and Java will like it. See what I mean? I can digitize the waveform and then just trading off space for time, make it part of the bytecodes when the compiler comes along to compile the waveform, and then I won't even need math.sine anymore because I'll have my sine waves in my sine tables, which gives me, the advantage of not needing a floating point unit. And also, if you think about it, if this waveform is in memory, it's got to be a lot faster to access than even if an Arduino had I'll call it a floating point subroutine library with transcendental functions implemented in assembler on an 8-bit controller, which would take up an enormous amount of space. It would also need to take a lot of time because it's simulating all the floating point functions. So you've basically, it's pay now or pay later. If you implemented in an 8-bit toaster controller the whole floating point library, including transcendental functions, I claim that it would take a number of CPU cycles to do the computation, whereas this is just a simple memory access. So for some kinds of computers, this is just better, if you have the memory to store a waveform. And adding a little RAM to a microcontroller is a whole lot cheaper than adding a floating point unit. You might as well, at that point, just switch to a 32-bit microcontroller. So my only problem with this is that first time through. If I equals 0, maybe we could say if I is greater than 0, and I guess that's kind of hacky. It is hacky, but that'll fix it. And there it is. So now I got myself a nice little array. It's formatted in Java format. Rich, I liked your idea. Yeah, I could then do a string replace, or I can proceed to use this hacky thing that I built here, whatever you prefer. It's really up to you. Yeah, string replace will let you change your curly braces to square braces, but you'll still need to do a buffer append with the int a array. At some level, you have choices, I think. Lots of choices. So now with n, you can make n as as large as you like. Here I'll change it to 100. That's probably going to be a lot more printing than you'd care for, but let's do that and see if it works. Array index out of bounds. Maybe my computation for n wasn't so good. Should that be 101? Oh, this is less than or equal to 2. That's what's doing it. If I go less than 2, this has to be, I see. This equal business, because I'm trying to seal the waveform, is messing me up. No? What's the error here? I++. It seems like the fixed audio data is just off by 1. Let's just make this 101 or something. It can't be off by a whole bunch, right? Yep, that's all it was. It was off by 1. And look, it's a big sine wave with 100 elements and carriage returns and everything. So you can just cut and paste that into an arbitrary Java program. You got your sine wave right there. And that's 100 samples. But if you wanted more, you could have more. The way I would do it is I would parameterize n. Let's make n equal to 255. Make it an integer. Make epsilon n minus 1. Oh no, it has to be n plus 1, doesn't it? Hack, hack, hack. And then remove the n from here. And what do we got? Yeah, my hacking leaves much to be desired. I don't remember if I should do the 1 and minus. It should be minus 1. Minus 1. Let's try the minus 1. That'll do it. Now we've got it. Yep. That worked. That's pretty cool, actually. It has the look and feel of a sine wave, doesn't it? Very, very siney. Sinier than other things that might be siney. Now, at the end of the day, you could convert your sine wave. What would you convert it into? You probably want to get your doubles back, right? Private, static. What would it be now? Int to doubles? Or, yeah, I guess that's right. Get, oh, I know. Double, array, get doubles. And the input is going to be integer audio data. So you'll have an integer audio data array of scaled sine waves going in, and then you're going to want to get your doubles coming out. So what you'll need for your doubles, double D array, equals new double array of audio data dot n. Oh, length. Sorry. So now I got to write a for loop for integer, I equals 0 while I is less than d dot length, I plus plus, and then d of I is going to be equal to, how am I going to convert my audio data? It's going to be audio data. Now, one thing I know, if I remember rightly, is that the audio data ranges from minus 127 to plus 128. No, sorry. Yeah, right. Let's write this down. So, documentation. Given data that ranges from minus 128 to 127, get data that ranges from minus 1 to plus 1. Now that after you write the documentation, it makes it much easier, right? So the input is, let's see, this is a double, I wrote my name, double D-O-U-B-L-E, double, I'm doing it again, double array, and this is going to be an integer array. Hey, what do you think of that? Does that sound right? Int array in, double array out. So you allocate the space for your double array, then you go through each element inside of the int array, and you know that it's going to be minus 128 to plus 127, so what do? You add 128, so now it's going from 0 to 255, so make this dot 0. You add 128, then you divide by actually, now that I think about it, all you have to do is divide by 128, and then it'll go from minus 1 to plus 1. Isn't that right? I think that's all you need. Tell me I'm wrong.
You're right.
Yeah? Divide by 128. So why is this giving me a hard time?
All you did is an array.
Oh, an array. A of I. Thank you. And now I've got my audio data, and I can return it. And what else? That's it, right? So now I can get my doubles, and I could maybe print them or something. Let's make this some reasonable number, like 10. And then what we'll do is we'll just get the doubles and print them. S out, Control J, enter. The doubles are reconstructed as end quote n paren sem print utils.print get doubles and input the audio data, which is called fixed audio data, and then how's that grab you? Good, right? Run. So the reconstructed doubles are, now here's the cool part, 0.63 isn't quite the same as 0.69, but it's close. So you lost precision. 0.97 is not the same as 1.39, 0.33. Well, we're getting very far off. At the end of the day, this was 0.64. Oh wait, here it is, 0.64. Am I reading from the wrong place? Because here's 0.63, there's 0.64. Here's 0.97, that's 0.98. We're actually very close. 0.85, 0.86, 0.33, 0.34. I'm becoming a believer, because look at this. 0.343 versus 0.342. That's what's this 0.85 thing doing here? Oh, that must be that 0.86. Yeah, I'm sort of thinking this reconstruction's pretty good. So the data is all in there, such as it is. I guess one could make a claim that we've lost a great deal of dynamic range by digitizing everything down to 8 bits, but at some level one could make a compelling argument that if you're in an 8-bit microcontroller, that's all you'll ever get unless you have, you know, the desire to do a little bit more heroic effort. And this is an error, because that should be an A, and it's an array. Oh no, I guess you could just put an A. Okay. So what do you think of that? Did anybody finish this integer-based discrete Fourier transform?
I did it in poorly constructed fashion.
You did it badly? But
well, I think I could do it better after reviewing this material.
Okay.
I submitted it online.
And you submitted it. Okay, great. Did everybody else sort of submit it with what's that thing called? Blackboard? Oh, you have a paper. Paper's good. I like paper. I'll take paper. Brody, how'd you do? Rich, does it work?
I had to keep the quotes on the pi calculation, but other than that, everything else was in. And the printouts on the last page seem to be pretty close.
Wow.
Kind of got weird in the middle, but it's
Yeah, I see that.
at the end.
It's very interesting. Interesting. Okay. Well, I'm going to look at your stuff, and I'll just sort of look it over and see what we're up against here. Are there any questions about this sort of homework? Was it interesting? Challenging? A little challenging. Too challenging. Kevin, your head's down. I can't see you. Was this challenging? Okay. Did you submit something online?
No, I don't.
Okay. It's going to be marked as late by the Blackboard system because I set up a due date, and it's kind of due now. Kinda. Sorta. Kinda. Sorta. I wondered if it would make sense to try and take the double data that we have here and try to look at it a little bit. So maybe it would make sense to do that. Let's extract the data into a variable which is called doubles, because I like that. That's a good name. Because what else are you going to call it? And then I thought, well, I've got graphing facilities available to me, and it might be fun to try and graph some data. And the way I graph data is like this. I call graph.graph, and I put in the data with an X label and a Y label, and then an overall description of what the data is supposed to look like. And so I thought it would be fun to sort of print out, well, let's see, the data and, bear with me a minute, and maybe graph it just to see what we're up against. And there it is. That is how my digitized sine wave looks. Now, one could make a compelling argument that that is a sorry excuse for a line approximation to a sine wave. But I say no, this is what happens when you re-quantize a double precision number into 8 bits worth of dynamic range. You get little, you know, what do they call it, edgy bits where the lines connect. Right? It's not no longer can you make the claim that this is infinitely differentiable everywhere, because there are point discontinuities. So when you talk about the continuity class of a waveform, their classification of continuity starts at C0. C0 continuity means that the waveform or curve touches everywhere. C1 continuity means it has a first continuous differential. C2 continuity means it has a second continuous differential, and that goes on indefinitely. C3, C4, C5 means you could derive it 5 times and it would still have a differential that's continuous everywhere. So differentials that are continuous everywhere are the kinds of things that we were taught when we first learned calculus. We would take a ruler and we would touch it to a curve and we'd say, oh look, it's differentiable everywhere. Then comes the rebels. The rebels come in and say, we want a class of curves that are differentiable nowhere. Curves that are differentiable nowhere represent the vast array of all curves you will ever encounter ever. You may recall, as undergraduates, when you first took your first course in stuff that's linear, they said, let's make the assumption that everything is linear. And then you found out in the real world nothing is linear, or almost nothing. And in fact, the class of things that's linear is like teeny weeny, and the class of things that are not linear is like everything else in the whole universe. And the same thing goes with differentiable, right? The class of things that are differentiable is like teeny weeny, and the things that aren't differentiable is like everything else in the whole universe. And so when you say it isn't differentiable and it isn't linear, it's like everything you know is wrong. Right? And you could say, well, oh, Professor Lyon, you're being hyperbolic again and you're saying this for effect. But it's true. And I'll give you an example. Here's a great example. Let's talk a little bit about noise. Everybody loves to talk about noise, but nobody does anything about it. It's kind of like the weather. So if you think about white noise, and there's like a wiki for this, white noise wiki, right? You can go to the white noise wiki and you can click on it and look, there's noise. And when you look at that noise, what you see is a waveform that is differentiable nowhere, but still has C0 continuity, right? I mean, if you look at it, every waveform is connected to everyone else, and yet when you listen to it, take a listen. That's white noise, right? So white noise is one of those classic things. It doesn't have a derivative, right? Because it's like trying to take the derivative of an asymptote. It just goes off into infinity. So it's got no continuity at all, and then it comes in with different flavors, right? What kinds of flavors? Oh, there's Gaussian noise, there's pink noise, there's white noise. You got noise all over the place. So if you want noise, we got noise. No question, noise is all over, and it's with us everywhere. In fact, one of the things that got Arno Penzias the Nobel Prize was the discovery of the background noise in the universe. That background radiation, or 4-degree Kelvin residual radiation, was the proof that there had been a Big Bang, and that it was like, I don't know, 10 billion years ago or something. Yes, sir?
What was his name?
Arno Penzias, Nobel Prize winner. He used to answer the phone, Arno Penzias, Nobel Prize winner. It's true. Arno Penzias. There he is. Yeah, and Robert Wilson. I always leave him out. Arno was like my boss's boss. He tried to get the video phone to work. I was there at the time. He was doing a demo. It was in an auditorium at AT&T Bell Labs in Murray Hill in 1986. He couldn't get the video phone to work. Back then they didn't have the internet. Back then they didn't have Skype, right? They had the internet, but they didn't have the web. Okay, let's put it that way. They had the internet for sure. They didn't have the web, because the web didn't come about till 1994, 95, with Tim Berners-Lee and the invention of hypertext transfer protocol and HTML. So this is all prior to that, and we were working on interactive television at Bell. And so Penzias, he had a giant scoop, a microwave scoop. Here it is. And he was trying to do microwave experiments so he could try and figure out how to do microwave transmissions, terrestrial microwave transmissions. And he was always catching in a bunch of noise. Now, he had a lot of problems here. You see this scoop? It's nice and dry inside. And you know what likes it nice and dry inside? Pigeons. And you know what pigeons do when they go in there? Poop. So he had a horn full of poop and pigeons, and it had this noise, and he said, oh, this must be full of pigeon poop. So he was going in there scooping out the poop. True story. And he said, I cannot figure out what the noise is. So then he went to the Princeton professors, and they said, oh, we know what this is. It's the background radiation of the universe you've discovered. And he said, yeah, I thought it was poop. And he said, no, important radiation. And so they said, yeah, I don't believe it. I think it's poop. So then they went back and forth on that a bunch of times. The Princeton University professors, physicists, finally convinced him this was important. And so then he got the Nobel Prize, and the Princeton University physicists got bupkis. Really, nothing. But you don't want that Nobel Prize anyway. That's blood money. That all comes from like dynamite and stuff. So if they offer you the Nobel Prize, just say no. Just say no. So, yep, noise. So important. Did that seem like a distraction to the main lecture? Because it really wasn't. It's important. Noise is one of those things that happens whenever molecules move. When don't molecules move? Molecules, and it can't move in a vacuum if it's a true vacuum because there aren't any molecules. Vacuum is the absence of molecules. So let's assume we have a non-vacuum situation.
Absolute zero.
Absolute zero. That's absolutely right. So as long as molecules move, we're going to have noise. If you have a resistor at room temperature, it is going to have a noise which is linear in temperature. It is going to have a noise that is a function of Boltzmann's constant. So in other words, at, let's say, 20 degrees C, room temperature, 70 degrees Fahrenheit, if you have a resistor and it has, let's say, a bandwidth that is equal to the audio bandwidth of your CD, let's say out to 20 kilohertz, then it's going to give you noise that's about 120 dB down from zero. So it's an interesting phenomenon. You cannot get rid of it. If you want to really build the cool stereo, take the whole stereo and put it in liquid nitrogen. That'll reduce your thermal noise floor, right? But your thermal noise floor is only going to be reduced by perhaps 170 degrees, minus 170 centigrade, I think. I don't know, whatever liquid nitrogen is. So it's one of those things where it's possible to reduce the noise floor, and in fact, if you build an infrared camera for looking into the universe, you will find that they often cool these things actively. They can either cool them with cryogenics, like liquid gases, or they can cool them with thermal electric coolers, or TECs as they call them, Peltier junctions. So noise is so important. Here's another one, and it's called pink noise. And there's my pink noise. Now what I did here was, and I printed the pink noise out, and I also rectified the pink noise. If you take something like this, which is just a bunch of numbers, and you copy them, you can bring up, what do they call this, Excel? And you can paste them on in. Maybe I just hit Control V. Yep, there they are. And now if you want, you can insert a graph, pie chart, scatter chart, whatever you like. Here's a nice scatter chart, and there it is. Now I went through the extra process of putting it in a Microsoft Office document, but I didn't have to because my Java program can pretty much do the same thing. On the other hand, if you want to cut and paste into Word and get your stuff out there and make it look nice and change the font and do all the things that Microsoft Excel can do, and maybe run some programs that can do like linear regression analysis or the kinds of things that you might like to do with data that may be easier in Excel, this is not a bad way to go. All you need to do is print a single column of numbers, and then you can copy and paste it straight into the Office document of your choice. Alright, so now if I go in through here and I said, geez, I want the average, I can just say, give me the average of A colon A, and there it is. So right now I see, aha, this noise that you have is biased. This bias, this is the average. It's supposed to have a DC bias of 0, but it doesn't. How do you unbias the noise? How do you make the average go to 0? Well, if this is the average minus 4.5 whatever, why not just take that and subtract it off? So say this is equal to that minus 4.5, enter, and then copy it and paste it on down. Yes, sir.
Plus, can you add 4.5 to all of those to shift it upward?
Yes, you do. Thank you. So if you said copy, oh I know, copy and then paste.
You can also drag.
Can you?
Yeah, just like that.
take this and then just drag it?
No, take the corner. Yeah, take the bottom right corner of the top cell and drag it down.
Like this?
Yep.
And then I can just do paste? Oh no, it just did it! How cool. So now, in theory, I should be able to take the average of B and now it's pretty close to 0. So I remove the bias. Right? And if I wanted, I could produce a standard deviation that actually moves along the array. But what I thought would be good is if we had a little lecture, get away from all this Java stuff. Enough Java. Too much Java. And I'm not going to save all that. And I'm not going to save this. And I'm not going to save that. I'm not going to save this. Instead, I'm going to do a lecture. And the lecture is going to be on an analysis technology called the Hurst exponent. And you may have seen a little, how you say, email. There it is. I had a nightmare last night. And the nightmare was I totally forgot about this class. I mean, like, really forgot. It didn't show up or anything. It's a classic insufficiency dream. You guys remember Dr. Sargent? Yeah, he used to have them too. This is what you get with people who are like overcompensating from their inferiority complex. So, thankfully, after I woke up, I said, gee, I better prepare a lecture. And hence the PowerPoints. Ain't it great? So the reason you're looking at these PowerPoints now, welcome to my nightmare. So Hurst is somebody who decided that they would try and examine a phenomenon called the flooding of the Nile. Now, one of the interesting things about the Nile River is that they have a history that dates back to the Egyptians, and they have an accurate history that goes back to about 600 AD. And what they're able to do is get flood data about the Nile and record it. And he decided, gee, wouldn't it be fun if we could do an analysis of the flood data? And so he did a statistical analysis, and he realized that there were trends that would allow him to predict when floods would occur in the Nile. And so hence the Hurst exponent analysis. And so what the Hurst exponent analysis does is it allows you to take data and decide about the data. If the Hurst exponent gives you a number which is equal to 0.5, the data is said to be unbiased. If the Hurst exponent gives you a number which is less than 0.5, it's said to be mean reverting data. And if the number is greater than 0.5, it's said to, in the world of the stock market, have momentum. When it goes up, it continues to go up. When it goes down, it continues to go down. Now, there's an interesting thing that people do without much justification when they invest in the stock market using a phenomenon called technical analysis. With technical analysis, they like to look at the price action of the chart and base their investments on predictions because of what the prices are doing. That works very well if the Hurst exponent is greater than 0.5, because when the Hurst exponent is greater than 0.5, the data is said to be momentum-oriented data. When it goes up, it continues to go up. So when looking at the Nile, and we actually find this to be true, this is kind of interesting, in the Bible, right? When you look at the Bible, people talk about how there would be good times and bad times, and how the bad times might last 7 years. 7 years of famine, 7 years of thirst, right? All these things. Well, they're grouping this flood pattern together. And so what's happening is Hurst is looking at this with an eye toward modern statistical analysis. And we're thinking that maybe the flood data is representative of a sample variable that comes from a random process. So a random variable might have to do with the flow inside of the river. And so what we wanted to do was we wanted to try and examine that and see if there was some mechanism in place that would allow us to make prediction. And so this is what Hurst tried to do. Remember when I said the idea of curves that were differentiable everywhere was combated by individuals who created curves that were differentiable nowhere? Well, when they started to do that, they coined a new term known as the fractal. The fractal refers to fractus, which comes from the Latin, and fractus means fractional. And so what Mandelbrot did, and he was a professor over at Yale until he passed away, was come up with a series of different curves that were fractional curves. Now, some of the people who are doing a senior project are doing fractal antennas. Interestingly enough, I happen to have one. And this fractal antenna is modeled on what's called a Sierpinski curve, and I'll pass it around for people to look at. And I just got it back from the fabricator. The fabricator is able to fabricate printed circuit boards down to what's called 8 mils. 8 mils. A mil is 1,000th of an inch. So 8 mils is 2/10 of a millimeter. But there are fabricators who charge a little more who will go down to even thinner than that. And there are some who will make printed circuit boards that aren't really boards at all, but are printed on top of 1 mil thick, mil standard, adhesive-backed material that you can just stick onto things like helicopter walls. And so this is one of those ideas that allow you to manufacture. I personally have manufactured over the summer 400 printed circuit boards, and really all you need to do that is a good design that can be made. They use Gerber files. Gerber files are like the lingua franca of printed circuit board fabricators, and you need a credit card with enough money on it to charge it. And then they do the whole thing for you, and they'll send it back to you in a box, and they'll even ship it like Federal Express or DHL. Well, you can pass this around. If you flip it over and look at the back, you'll see it's plated through, and it's copper. And what they did, and this is kind of marketing, is they ship it in purple, and then they use purple solder mask. So they make purple boards. It's the only fabricator I know that makes purple boards. I don't think there's any particular advantage to having it in purple, but there it is. So Mandelbrot comes up with this idea of creating a series of curves, and I implemented this one in the printed circuit board so we could make fractal antennas. And then he proceeds to characterize the curves using a non-topological dimension called the Hausdorff-Besicovitch dimension, which everybody abbreviates as H. And so what you're going to do in your next homework assignment is you're going to do the computation of H indirectly, and it's going to be called the Hurst exponent. And so what I'm going to do is I'm going to show you how you can do that computation yourselves. And you can apply it to a whole bunch of different signals, including biological signals. So when you think about the biological signals, think electromyographic signals, let's say the electricity that comes off of your muscles, which some people use for powering prosthetic devices, the EEGs, the EKGs, maybe temperature, your breathing, all these different things that are signals inside of the body. And so what you can do when you do these analyses is you can try and characterize the signals using a variety of different statistical or analytic techniques, including Fourier transforms. And this is just one more means of doing that. So if you have truly random data, that is white noise, I would expect your Hurst exponent to be equal to 0.5. If you have, well, let's say mean reverting data, what some people call anti-persistent data, then you're going to have an exponent less than a half. And if you have reinforcing data, that is momentum-based data, or what some people call persistent data, then it has an h value greater than a half. If you start with white noise, I expect it to be 0.5. And what you want to do is you want to start by computing your average, and that average is important because it gives you what's called, in the voltage world, a DC bias. So if you have a sine wave, right, there's still power there because it's AC, but it usually has a 0 DC bias. And so what you're going to be doing is removing the DC bias from the observed data set. So compute the mean over the whole available data. Then what you want to do is you want to come up with the variance computation, which is basically just taking the data at one point and subtracting off the mean, and then summing up all of the standard deviations. Then you can do this over an arbitrary subset of the data. So when you look at the sigma in here, it's going from I equal 1 to n, and then it says k for 0 less than k less than or equal to n. You can change k, the total number of points that you want to use in your analysis. You can basically say, I'll do all of them, then I'll do every other one, then I'll keep skipping. I can change what's called the radius d-ball of the Minkowski sausage. That's what that is. I can do it this way. Let's see if we can do it. I'll get a pen. Yes, here's a pen. And now I'll draw a waveform. Actually, that's a very poor drawing. I need a different waveform. Let's try this. Ah! Do you want to keep your ink? No. Discard. Keep. No. Keep! Ah! That's okay. Discard. Now I should be able to insert a new slide. New slide. There we go. And go. Okay, so now I'm going to do my little pen. So first thing we'll do is we'll draw an axis. Then what we'll do is we'll draw a jaggy waveform. Now, if you want to compute the length of this waveform, there are a couple ways you can do it. One way is you can use circles, and then take the circles and connect them. And if all the circles have the same diameter, and they don't here, but they should, then what you've got is a way to compute the length of the waveform by counting the total number of circles. These are called the radius d-balls. If you subtract off everything inside of the circle and just leave the outside of the circle, what you get is something that kind of looks like this. That's called the Minkowski sausage. So what you want to do is you want to figure out what the length is of the waveform as a function of the circle, and you plot the length divided by the total number of elements in the circle, total number of circles, and then you do it again. Only you change the number of the size of the circle, and you do it again, and then you do it again, and then what you do is you draw a line through it, and the slope of that line is 1 minus d sub h, known as the Hausdorff-Bessy-Kovich dimension. So what you're doing is you're looking at the rate at which the line increases in length as a function of the total number of elements in your Minkowski sausage. And that's how you do a Hurst exponent computation as well. So when you're looking at something like the formula that's here, it's inspired by the deviation away from the mean and also the total number of elements that you're planning on using when you do your Hurst exponent computation. They also want to compute the range, that's just the Vmax and the Vmin, over the interval, and then they give you this the standard deviation divided into that range. So here's R, here's the standard deviation, and then you want to change the total number of elements. That changes the radius of the d-ball size, and you do it again, and you compute the log of R over S. And then you get the log of n, where n is the total number of elements that you plan on doing the comparison on. So you get those points, x and y, and then you fit a line to those points. And then you get the slope of that line. Since the points are kind of all over the place, the line that best fits is formed by doing what's called a linear regression. So linear regression is just a way to get the line that best fits a series of points. This is kind of what they're about. There's your radius d-ball, here's your Minkowski sausage, and here's how you compute the slope of log. I guess I better not try and draw in that some more. I just keep screwing it up. So what you can do with these Hurst phenomenon trends is you can sum them up as a function of time and see how they change. These are flows over different points in time. And here's what Hurst did using his Hurst notation, which, you know, is kind of like the notation first presented, but somewhat different. I guess notation's a constant battle, but it's not too bad, because there's the Vmin and the Vmax over in here. And here are some sample notations, sample results done with what's called a random normal distribution. And then here's the Hurst component being computed for what do they call this program? It's Wolfram's program. I think they call it Mathematica. So I thought that was kind of cool. Now you can see the straight line approximation. This is log of the partition size over log against log of R over S. Now, what I did was I emailed everybody some implementation of this whole thing using MATLAB. And I also was very careful to check to make sure that somebody didn't already have an implementation available in Java. So in MATLAB, what they do is they call some subroutine called Hurst exponent, and then they throw in some random data, they plot it, they estimate their Hurst exponent, and then they printed out the results. This is the MATLAB code I mailed to you. For MATLAB, you know, I'm really not a MATLAB expert. Is somebody here who really knows MATLAB? Kevin? No? Rhodey? Not so much? No? Nobody? Nobody knows MATLAB. Good! Then we'll all learn it together. So, alright, because that's why we go to university, is for learning. I actually, to be honest, I did use MATLAB for a couple of courses. Oh, it was in the late 80s. So I might have forgot it because I haven't really used it since. So this looks kind of like some kind of data structure being allocated. Size of data, m to n points. I'm guessing they're just making up some data, and these look like the x and y points, and that kind of looks like some data, and I think they're going to copy data 0 into data 2, but I'm not sure about that. Here's this thing here called bin size, and if you're thinking in terms of the radius d ball, I'm thinking that's what this is. They're going to keep changing the bin size by a factor of 2. And then there's a while loop that starts off that makes sure you have at least 4 points left. And then the core of the while loop looks like this. And now he's got the bin size here. And if you look at how bin size is increments, it starts off as 1, then it goes to 2, then 4, then 8. Right? It keeps doubling in size. That's the d-ball sizes that he's using. And the number of points that he's going to work with keeps halving in size. And then he's writing this for loop. Now if I looked at this for loop knowing nothing, I'd say for I equals 0 while I is less than the number of points. And now this thing is a percent. This percent I'm thinking is a comment. Average adjacent points in pairs. So that's all part of the same comment. That's what I'm thinking that is. So this is basically just saying for I equal 1 to the number of points. If I was in Java, I'd say I equals 0 to, well, I is less than n, I plus plus. I'm thinking that's the equivalent. And then here comes data to a point. So this is like, if I was doing this in Java, I'd make this an array. Okay, that's fine. And then I can sort of see 2 times I points minus 1. This is kind of what he's talking about, the averaging of the adjacent points. So what he's doing here is he's just sort of averaging 2 points. Why is he multiplying it by 2? I'm not sure, but that's an index into an array. Where did he get the I points number? Oh, that's this thing here. So that's in the for loop. And so he's made a new array, data 2, and then he copies it. And now what is he up to? I guess he's computing his logs. But why is he doing this? That I don't know. So this MATLAB doesn't make a whole lot of sense to me. If there's a good way for somebody here to convert MATLAB to C or Java, I'd love to know it. Wouldn't that be swell? And then here's his linear regression fit, all of the logs of x and the logs of y. And you know, if you could just print out the logs of x and logs of y, that would be fine. You wouldn't even have to do a polynomial fit. But if you wanted to, I've got a regression fit program. And there might even have one in Excel. I think there probably is. Excel does that sort of thing. But I'm not real sure how. You guys are probably better at Excel than I am at this point, especially after that last thing where you could drag the corner. I didn't know about that. That's a good one. And so that's the shtick. Now, if you wanted to keep, discard, keep, discard. I don't need it. So then, if you wanted to do it so that save, don't save, 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 save. No, don't save. Compatibility checker. Ah. Don't save. Ah. Too many choices. So if you wanted to, you could find like a regression analysis, and if you look under math and you look at approximations, you can see like this curve fitting over in here. And there's a linear regression analysis program, and it's all there for you. And you can see where it says linear regression. It'll give you can give it the points going in, and it'll return a function which is going to be something that does a computation with A and B. And so there it is. There's the function. So what that does is it creates what's called an anonymous inner class, which is going to evaluate x as a function of the slope and the intercept, and give you sort of the line approximation that goes through the given points. So that's what this function does. And we could try this out if we wanted to. But in any case, it's doing the linear regression thing. Given a set of points, it gives you back a function that creates a line. So the locus of points pumped into here will give you points that are on this line. Although, if you think about it, what you really wanted was the slope and the intercept. Why would you want a function if all you want is the slope and the intercept? Right? Anyways, there's a couple of ways you can do approximations, and slope and intercepts is just one of them. So if you wanted a polynomial fit, maybe you really would want a function coming back, because you're not sure how many orders you're going to need for your polynomial fit. Right? So if you said, oh, I want a fifth order polynomial, pretty soon you could have an nth order polynomial. Maybe you should be returning a function that takes a point in and gives you back the approximation back. So I can sort of see why you'd want that. Linear functions. Yeah, here's a polynomial. Here's a least square fit. Here's a cubic spline. Here's a Hermite polynomial. What do you think of that? You guys ever do a linear regression fit before? Yes. How do you do that in Excel?
I've never done it in Excel.
Oh, how do you?
Oh, well, yeah, of course.
I don't know.
If you make a graph, then it's really easy to get a
Yeah?
linear regression.
Okay. Shall I take your word for it, or you can just tell me? Here's a pile of numbers. Here's a Microsoft Excel document. Paste it in. I'll make a graph now, huh? So I'll do insert line graph? Scatter? Scatter? So here's my scatter graph.
You want to right click somewhere. Right click away from the data. Data.
Is this one of those things I should be Googling?
No. It's somewhere in the options too.
Oh yeah?
Yeah.
Well, I'll take your word for it. But I was thinking, wouldn't it be fun if I did a linear regression fit to this data using Java? But actually, I'm very happy to see you guys do it with Excel. It wouldn't bother me if I knew how to do it. It's one of those things that I hardly ever do.
Yeah, likewise.
So if you don't do it, you lose it, I'm sure. Linear regression. Huh? Yeah, trend line.
Yeah, right click one of the points. Like on the point, select the point.
Linear.
Maybe you want to say your intercept instead of
You could display the.
Oh, there you go. Very nice.
You could display the equation too.
Excellent. That's easy. Yeah, sometimes it's not worth using Java. Sacrilege, right? Well, I mean, really, if you all you have to do is hit add trend line. So you're saying I can get the equation off of this?
Yeah, go back to format trend line. You got it. Display equation on chart.
Oh, wow. How cool. I like it. So, does it make sense to try and do this again with Java? Or no? It's just a subroutine. Yeah, what's the point? Well, I thought that was fun. Is it break time? I think a break would be good. Alright, so let's take a break. So for next week, I was hoping that you guys would write a program in Java that would compute the Hurst component. And if we go to... oh, shoot. He wants me to log in again? If you go into, I think it's content. Right, there we go. Write a program to compute. Let me see if I can make this a little larger. There we are. To compute the Hurst component from 100 samples. And you can read about the Hurst component here. This describes the Hurst component. In theory, it should be 0 for white noise. White noise is here. Should it be 0 or should it be 0.5? I think it should be 0.5. I don't think that's correct. I think it should be... I don't think it should be 0. So here's the... here, made it a little larger. The Hurst component and a little explanation. And then you could see positive autocorrelation. I like my explanation better. Positive autocorrelation. 0.5 is uncorrelated. So white noise would be uncorrelated. And here's the same notation that I was using, pretty much. Rescaled range and time span. R is the range of the first n values. S is their standard deviation. E is the expected value of the range divided by the standard deviation. N is the time span of the observation. Number of series and data points. C is a constant. To estimate the Hurst exponent, so there's a nice little explanation here. Calculate the mean, then adjust the mean over the entire sequence. The cumulative deviate series. That's going to be the sum of the standard deviations. Compute the range R. So you want to find the maximum number versus the minimum number over the given number of elements. Then compute the standard deviation. And then do the division. So it's a bunch of statistical computations, really. And I can help you get started with some of it. What's the rest of this? HQ equals 1/2 for brown noise. One gets 1/2. I guess that's what they would call white noise. Rectified white noise would be, he's calling it brown noise. It's a random walk or a Brownian distribution. Let's start by doing that. Let's create a random walk. We'll create a random walk by taking white noise and rectifying it. I think that what we'll do here is we'll make a new Java class and we'll call it a random walk. Okay? Let's do a random walk. So with the random walk, I'll just write it all in a big main method, and what I'll do is I'll say something like this. Double D array equals get random numbers, and I'll put in 100. Now, before I write something, I like to check to see if there's a program that's already there that might help me. So I go to the math package and I look for statistics, statistical utilities, or math utils, or something that could just sort of help me out with this. And what I'm going to do here is I'm going to show the members of each class. And I just want to see if there's a way to get a series of random numbers. And there is. And it says get random double data. And when I look at it, I was about to write this, but I realized I'd already written it. It inputs n, which is the total number of elements you want, allocates some space, and then sets up the data. But you see what the problem is here? Is random is a number that ranges from 0 to 1, I think. This is going to multiply it by 10. I'm not so keen on that. So maybe what I'll do is I'll write my own little function that's kind of similar. Get random unit data. And I'll forego this business about multiplying by 10. But all I really wanted to do was avoid having to keep rewriting this for loop. So if I can call something like mat1.getRandomUnitData, that ought to give me like 100 numbers. Now what's this problem? Oh, import class. There we go. And so now someone said that I could print out the data with sout control. What is it called? Arrays dot to string, and then I could just put in D. Alt enter. Oh wow. Thank you. It's like a gift. This is not the same program. Okay, so here's a bunch of arrays. Here's a bunch of stuff. Let's print it because I don't really know what that looks like. Graph.grapher. See, graph.graph D, and then it'll be x. Let's see, quote x, quote y, and quote and then this will just be kind of like random. Now I got a problem with the quotes. Something's going on here. That quote goes there, this quote goes over there. I don't really want to print it after all. I'll just look at it. And then there we go. That looks like random stuff. So there's my random numbers. What do you think of that? Now let's make a random walk out of it. And the random numbers are kind of interesting. It looks like they can be 0 or 1. But they don't go negative. Isn't that right? They're not negative. So what I'd like to do is I'd like to give them a 0 bias. So after I get the random numbers, I'd like to get the average. So what I'll do is I'll say something like this: mat1 dot get average. No? There should be like statistics that give me the average. Let's see if I can get the average. Oh, get mean. Okay. mat1 dot get mean. And then put in the double data, and here's the mean. Double. What do we call the mean? M? That's a good name. And so then what we'll do is we'll take double D and we'll set it equal to mat1 dot subtract. Maybe add a negative. Subtract, and then it says from D M. So that'll subtract off the average, and that'll give us an unbiased, that is no DC offset. And there it is. So now it's ranging from minus 0.5 to plus 0.5. No DC offset. Now what I'll do is I'll make a random walk out of it. So double walk array equals new double of D dot length. Oops, there we go. And then I'll define a sum variable, double sum, and set it equal to 0. And then what I'll do here is I'll populate the walk by walking through the random numbers for integer I equals 0 while I is less than D dot length I plus plus. And what we'll do is we'll say that the walk of I is equal to the sum. And then we'll let the sum equal to the sum plus, and then the walk location will be altered by the random number that comes in. Now we know there's 0 bias, but what we're going to see is that the changes in the random number are going to cause us to drift up and down. And we'd like to eventually get home, but we may not be mean reverting. So let's find out if we have a biased random number sequence. So what we'll do after we print a graph showing the random numbers is we'll print the walk. So then we'll walk the walk. So this is what happens when you do rectified Brownian motion here. See if we can get... And so there's the walk, and it looks like quite a different thing, doesn't it? Right? Over here we have the noise. But over here we have the random walk. Now the interesting thing about the random walk is that when you show it to people who do technical analysis in the stock market, is they think you're looking at a stock price. And if you know anything about literature in the world of the stock market, you know A Random Walk Down Wall Street is the name of a famous book. So here we go. We can now see the random walk is representative of Brownian motion. And Brownian motion is one of the things that Einstein studied and wrote some interesting seminal papers about. Einstein was not an experimentalist, but someone who had studied pollen floating around on water noticed that there was this interesting Brownian motion but couldn't understand it. And so what we're really looking at is evidence of an underlying random process. And the random process is causing drift of position, and this is the random walk. So on the left is the random input, and on the right is the random walk that comes back from the output. And it truly is a random process, as you can see, right? Because it was white noise going in, but it's a, I'll call it Brownian noise coming out. Isn't that interesting? And so now, let's see if we can do a computation of the Hurst exponent on 100 samples of the Brownian noise. And so, you know, if you look at it that way, it should be possible for us to look at this Brownian noise and figure out what the average is, subtract off the average, and then proceed to get standard deviations. Would you get a different waveform if we took these input signals, which are supposedly random, and shuffled them? What if we took the same exact data and reordered it? Wouldn't it be a different waveform? It would look differently, right? So what you see right over in here, it's kind of looking like a trend line. Those people who do technical analysis, they would draw a linear regression right through here, and they'd say, oh, look, it's persistent data, right? It looks like the Hurst exponent is greater than 1/2 locally. And so I think that's kind of interesting. What do you think of this little code here? Can everybody kind of understand it? It's simple enough, right?
I'm not sure exactly how you got it to get the negatives in there.
Oh, well, I first computed the mean off of the random numbers, and then what I did was I subtracted the mean from each one of the elements in the random numbers and came and replaced the random numbers. So the average value was probably something like 1/2, and so what I had done was I had subtracted off 1/2. I don't actually know what the average value was, and so that allowed me to remove any DC bias off of the input signal. So I mean, I could probably have done something like this just to make it clear. The average prior to subtraction was M. So here was the average, almost 1/2. So the random numbers were giving me numbers that range from 0 to 1. I had 100 of them, and my average was about 1/2, which kind of makes sense. And so then I just subtracted off 1/2, and so now I'm getting numbers that range from minus 1/2 to plus 1/2. So that removes the DC bias. I could even have written that here. Remove DC bias. so the DC bias was like half a volt. And then for the random walk, I just did the summation to see if there was local bias. And you could see local bias because there was trends where things would go up, but then they would end up going back down. So overall, it was mean reverting. But at the end of the day, you could see local trends. Right, so here it is going up, but then it goes back down. On average, look, it starts at almost 0, it ends at almost 0. If you buy and hold, you will earn nothing, or almost nothing. But if you were to buy and sell whenever you were up 20%, when would you buy again? And if you sold, if you could play all these interesting games. What if you buy when you're up 20% and sell if you're down 5%, and buy again if it goes up a little bit later? You can try all these different trading rules. So you can back test this data and see if the different rules, when you run for different random numbers, behave differently. At the end of the day, you just generate a lot of churn, and you lose money on commissions. Is there any, if you saw this stock and you just looked at the price, is there any fundamental reason to buy the stock? Right? Right? We don't know what the product is. We don't know what business they're in. We don't know what the economy looks like. So if you think about it, without any fundamental reason to buy the stock, trading it just based on this random behavior isn't likely to earn you any money. So according to my little guide in here, I'm supposed to calculate the mean. Right? At this point, I could say the mean is probably 0. Right? That's the overall mean for all n. But should the mean be calculated for a partial time series or the whole time series? See, we did it for the whole time series. If you do it for a partial time series, then what you're doing is you're grabbing a chunk, like the radius d ball, that only grabs a little section at a time. So you could grab like 5 or 10 components at a time, and then do the radius d ball mean computation. So I think that's what's interesting about the MATLAB code, is he used a radius d ball that increased as a power of 2. He went from 1 to 2 to 4 to 8 samples, and then he went to 16 samples. I think it's very interesting that he changed the radius d ball in powers, because when you do a Hausdorff-Besicovitch fractal dimension computation, they're normally silent in terms of the size, the rate at which you change the size of the d-balls for making the Minkowski sausage. So I got a few statistics available to you in the math package, and you're certainly welcome to use it. Let's see what else we got here. Here's the stats. This will get you the variance. This will get you the standard deviation. What else will you need? I think that's it. Yeah, the moving averages, the simple moving averages. Let's see if this works. Yeah, this one's good because it gives you an arbitrary start point and end point. So if you're looking for an average, starting at any point in the data and ending at any point in the data, then you have a mechanism whereby you can get a traveling windowed average. So that may be of some use to you in this particular case, because you're taking subsets of the data. And so then your question is going to be, okay, how big should the radius d ball be, and how should I change it? If we follow the MATLAB example, you keep going up by powers of 2. I'm not convinced that that's the way you should do it. It's certainly a way to do it. The funky thing about this is every way I've seen of computing the Hurst exponent gives you slightly different answers, which I find really bothers me. There's like 7 main ways of computing the Hurst exponent. Yeah, here's an example of how you would test the simple moving average. And if you look over here, it's 1, 2, 3, 4, 5, 6. So what this is doing is it's giving you a simple moving average starting at 0 and going across 6 elements. So you can start at any location and do 6 elements. As long as there's 6 elements left, you won't have a array index out of bounds exception at runtime. Let's see if we got a here's a variance. You know, one thing that I like to do, I think, is just make copies of the data. Then if you have a copy of the data and you pass it into variance, you know it's not going to go off the end. But then you're constantly chunking the data out and passing it into the variance, let's say 6 elements at a time, and making copies and reallocating them. But one way around that might be to allocate like 6 elements in a window and fill them, and then reuse the same 6 elements. So if you wanted to get the variance 6 elements at a time, I'd say reuse the same 6 elements when computing the variance. You need to see an example of that? So I'll make a few notes. Use, I think it's called stats.variance. No, that's it. Get variance, copy. And reuse the elements in a window, n elements at a time. And what else do you need for this? Oh, there was a stats.sma will give you a moving window average. But maybe if you've got the ability to chunk out little pieces, you don't need a moving window average. But there it is. You can use mat1 get mean to get an average, or use mat1.get mean. What else? You've already seen how to do some simple graphing. I think that's enough. What do you guys think? It's pretty straightforward. If I wanted to take out chunks of data, n chunks at a time in a window, I might do something that lets me walk through the series. So I guess you guys can figure out how to do that. That's a doubly nested for loop. What else? There's the standard deviation, so you know how to do that. And the sum of the standard deviations, you can compute that. What else do you need? That's it. It's a straightforward computation. I'm hoping you guys can do it. Should we look at the DFT? Rich, should we look at your code a little bit and review this homework? No? Do you have it electronically? Is it up on Blackboard? Is there like output here somewhere? Oh, that's the one where it gives us some funky output. Yeah, it looks like it sort of worked because you got a reconstruction. It just wasn't quite right at the beginning. Oh. Yeah, the Arduino function for scaling is suspect. Huh? Yeah, I used it before, but then I always wanted to know what it was doing. So then I dug into it pretty deeply to look. I forgot now, but yeah. I kind of like having the code for everything.
There's a method, I think it's the second method on the first page, is the scale.
So it says here, this is where you computed 2 times math.pi over n. And it looks like you did that because, oh, wait a minute, you used math.sine as well, and math.cosine.
Yeah, so but the only ones that were kept as quotes were anything based on that pi calculation. Everything else I just passed it out.
Yeah, the way I would have done this is I think I would have converted the I would have digitized the cosine and the sine. Because the waveforms needed to be requantized. I mean, you don't have the luxury of calling math.cosine and math.sine. You got to take off? Okay. Yeah, this is not quite right. But it's a valiant attempt. Yeah, so what Rich did was he left his cosine and his sine trig functions in place, which I was hoping you guys could digitize. Looks like you left math.pow in place as well. But you took it to the power of 2, which means all you had to do is a shift, a right shift. And then you wrote an error. This is so close to 0 that every time I tried to work with it in int, my whole data set became the same number and caused an error in my scale method. Oh. So we're not quite there yet. I'm surprised there isn't something already on the web. Isn't there already an integer FFT? Yeah, I thought this was already done.
Who wrote the paper?
Who wrote the paper?
No, it was on your website, but it wasn't. You didn't write it.
I wrote the paper?
Oh no, I think I saw that.
No, you had a PDF on your site.
Yeah, it was on .java. It showed that .java wrote it.
It was someone.
Under papers?
No, it came up in a Google search.
Yeah, that's how I found it too.
search. Yeah, I can do a search this site, and I can do integer FFT. Oh, look, fast integer Fourier transforms. Somebody already did this. I had a feeling. Keep integer FFTs. So you can actually can you implement this algorithm?
Yeah, I didn't understand it.
Oh, you didn't understand it.
And it was an FFT, so that's odd.
Oh, he's using lifting coefficients. This is interesting. Gee, I should put this on my website. Number of coefficients and bits. FFT. Well, this is an FFT. I only wanted you to implement the DFT.
Yeah, I stopped reading it.
That's a good paper, isn't it? Look at that. Oh, this guy must be smart. Okay. That's very nice. So there's but here's another one. What's this? Oh, complex FFT, complex factorized real FFT. Oh, I don't have an integer FFT here, do I? You know what I have is an integer wavelet transform called lifting. But I don't think I have an integer DFT. Oh, FFT course for FPGAs. That makes sense. See, those guys are going to need, yep, fixed point FFT. Yep. Now, the only trouble is it'll probably be in like VHDL or something. But on the other hand, that might not be too bad. This thing runs at a gigasample per second on a Vertex FPGA. That sounds like fun. So what do you have to do here? Buy it? Yeah, this is like something you gotta buy. FFT core implementations. Yeah, we could do that, but it'll only run on a Vertex processor. On the other hand, it runs at a gigahertz. I actually think I have a Vertex core processor sitting in my office, although I probably moved it out to Banner 133. Alright guys, I'm liking this idea of buying the FPGA software, but I'm thinking I'm still not going to have it in Java. And I really wanted it in Java. So, should we just do it? Do we have time? I don't think we have time. I have a feeling this is going to take time. It was one of those things where I was kind of psyched to do it before, but if you guys think it's just really hard and you don't want to bother, I won't. J transforms. Where did my DFTs go? Under here, Fourier transforms. DFT. Fixed point. Integer DFT. Did somebody like do this already? You guys didn't see this, right? Oh, too bad for you. So here is a sine that uses integers, and here's a cosine that uses integers. Here's log to the base 2 that uses integers. Gee, this kind of looks like it's already done. Oh boy, I bet you're all pissed off at me now. Sorry. Well, Let that be a lesson to you. Always check my code first to see if it's done already. Oh wow. Hey, look at that. Gee, somebody did this already. It's an FFT radix 2 on 16 points in an integer. Oh, it's even an FFT, is it? Is that right? Wow. No, it's DFT. Let's see now. So you see what I did here? Cosine is all integer. So it was scaled, but it wasn't stored in the integer array.
So you still did a double calculation of something.
Yeah, but you know, if the integer's going in and an integer's coming out, it'd be a relatively simple matter to fix the sample size in advance for your cosine and your sine, and then digitize it to store. So what I claim is that the number of different integers getting passed into the cosine is relatively small. Now the question of how small that is, I don't know. Oh, n. And this is 2 pi ij on n. And what gets, how does one compute that? Okay, so here's where I don't know. I'm going to say this is a relative truncates. You have to know in advance how many samples you're going to do. N is going to be the size of the sample data. So if you had 256 samples, then you'd only really need to do 256 samples off your sine wave. That's what I say.
At the same time, that calculation,
Yeah?
if you're storing that as an integer, doesn't that just truncate down to 0? That's where I had trouble.
This here?
No, that 2 pi, the one you had before, 2 pi on n.
2 pi on n, does that truncate it to 0?
We had 2 times pi divided by n, so if n is 256, that's really small.
Yeah.
Well, I don't know. Let's see what happens here if you oh look, it prints out n. Do you want to print out this thing?
Yeah.
Yeah. I was actually doing this.
So that's every time that turned out to be 0, that's why I was getting similar numbers and then it just truncated off.
Hmm. 2 pi on n. I put it in as 392. 2 times pi. Let's see. Pi is 3.1. This came out to 3.93. What would that mean, 392? N is 16. So I'm only doing 16 elements. I suppose I could do something with more than 16 elements, right? 2 pi on n is it's scaled, right?
Yeah, what did you use for pi?
Blew it out.
What did I use for pi?
Yeah, you have a variable called pi.
Yeah, I do. Let's find out where pi is set. It's scaled. It's a scaled version of pi. And scaled, it looks like it goes in and multiplies by my scale factor, which is 1,000. So if you're going to use pi, take the number pi, multiply it by 1,000, and you still have the number pi, only it's truncated down to, I don't know, 3.1415 or something.
So you have to scale everything now.
Yeah, everything has to be scaled. You need a scale factor in there to decide what your dynamic range is going to be on your integer. Because at the end of the day, you do want to multiply by 2 times pi, but it'll be a scaled version of pi.
I think what I did was I scaled it after, I tried to scale it after I saved it as an integer, so it was already 0.
Oh.
So in my calculation, I took scale pi for everything.
Yeah, I think so, because otherwise you're multiplying by some kind of
So it's just 0 for
0, right. If you or you multiply by 3 or something, I don't know. Yeah, you got to preserve some dynamic range, and 3 significant figures off of pi is probably sufficient. I could probably print the intermediate numbers, like these numbers here. This should range from 0 to 2 pi. S out, Control J, enter, quote, paste, end quote, plus, paste, and what's that buy you? So, okay, here's the interesting thing, I guess. It's going from 0 to 2 pi, and incrementing and then back to the cycle. So this is cycling right in through here. A scaled version of 2 pi jk on n. And so you can see it's cycling through. So I guess that's my solution, such as it is. If I wanted to, I could change this to be an arbitrarily large sequence. So suppose I did that. Test DFT, and we'll make n larger than 16. Let's make it 64. I think it'll work. Yep. So you can do a DFT for 64 elements. So if you can do 64, maybe you could do 256. That's pretty cool.
Under 0,
Yeah, this says 257 and the input was 255.
yeah, your 0 one.
Yeah, things are not quite right. Let's go to 0 and see what happened. Because you had problems at the beginning too. Here my 0 is minus 20. Now it's 6. Now it's 100. I think my scale factor has to increase. I need more dynamic range. So we'll use an extra bit or so, and then run it again and see if that improves matters. Uh-oh. Well, that screwed everything up. I might have a problem with scale factor in terms of dynamic range of what I've been using. Is this ints? Ints should have plenty of dynamic range, I think. Right? 2 to the 32? That's like a big number. Isn't it? Big. Big. So there's probably a bug somewheres. Here, take that down. Take that back. Scale factor of 100. I wonder if I assumed it. I don't like to hard code these things anywheres. What else could I be doing wrong? Where do I begin? So n, where I was doing the test. Find test. Control B. Stop that. Control B. Let's get this back down to some reasonable number, 128, and run it again. Something broke. You see, it got really wrong as it got larger, and I went outside of my dynamic range. I have a feeling I needed longs for this. Let's try it with 64. 64 is a good number, and I'll tell you why. It doesn't push the limits of your microcontroller, although things are looking kind of wrong in here.
Yeah, I was noticing after 32, I wasn't getting that good coefficients.
I think on mine, upper half, except the last one.
Yeah, this is not correct. 33? This is wrong on so many levels. What about 32? 32 work any better? I thought this was working. Now I'm trying some tests and it's not working so good. Here, 35, 32, 37, 27. It's sort of out of sync. Here's a couple of ones. You were getting that.
Yeah.
9, 11, 10, 5, 0. Yeah, this is looking pretty sorry. Okay, I take it back. This is hard. Why is my integer DFT so crummy? I think it should be better, but I ran it with an N of 16, I think, and a scale factor of 1,000, and things were fine. Or were they? Now it's not looking so good. 17, 14, 15, 14, 9, 10. The 10 is correct. Then it goes up 12, 5. It's kind of looking messed up.
Can I see what you do if you put 8?
I think this is an artifact of digitizing your sine waves badly. Because you see some of those sine waves going like this. And if you have only 8 steps for your sine wave, that doesn't seem like enough resolution for the sine wave. I think sine wave resolution should be better than the input waveform resolution. I'm thinking. But I might be wrong about that. What I've done here is I said, okay, we're going to input signal and we're correlating it with with a kernel, and the kernel is going to be digitized to only 8 samples because there's only 8 samples on the input signal. That kind of sounds messed up. I could sort of see why that might be messed up. Well, it's a good challenge. I'm glad you guys tried it. You got interesting results. I don't know that your results are any better or worse than mine. You did 30? I'll do 30. Let's see if I get what you got. Well, we're going to get different results. We took a totally different approach. Test FFT. It says DFT. You tried 30? Yeah, that's not an integral power of 2.
No, I mean, I did 30.
32. Don't you want an integral power of 2? Yeah, it's kind of whacked, man. But I'd accept a whacked answer for something like this. I mean, you're just doing all these sort of weirdo things with the FFT, with the DFT, right? You're digitizing sine waves, you're approximating cosine waves with sample waveform tables. You know you're not going to get back the original signal. There's just going to be too much error. But that's good. I mean, that teaches you something. You know, there are limits to what you can do numerically, and I think that's good to explore it. A lot of people get very interested in things like what I would call round-off error and precision. And I think this is one of those areas where you really get into the limits of what it is you can do with integers. And you're at the edge of it. Doing FFTs with ints, it's not easy. People write big papers on that stuff. Big brainy people with so much brains they got to wear them like in a pouch around their belt. They just kind of stick out. So
Getting pretty good results actually.
you're getting good results with
Yeah.
integers?
I made my scale factor 1,000 instead of 10,000.
Well, I think that's what my
I had a
scale
slightly
factor
different
was.
approach,
Different approach from me?
though. Yeah.
You gonna upload that to Blackboard or
It's
send it to
it's
us?
already there, but what's in there is it's at 8 right now and scaled to 10,000. I'm getting better results scale 1,000, and I'm trying 64. I got good results. I'm trying 120.
Okay. Well, I would say this about that. I'm very happy to see somebody come up with a good integer DFT algorithm, or at least implementation. In theory, you know, it shouldn't be rocket science, but in practice, it's just not easy stuff. So I gave you a bit of a challenge problem, but that's okay, because you tried it. And I'm always happy to see attempts. And I don't expect things to be accurate. I personally didn't have a great time doing it. Had problems, but that's okay, Got to try these things. So listen, that's all I have time for today. You've got a Hurst exponent computation homework, which I think is fun. You're going to try and do the computation on this rectified Brownian motion, which we derived here in class. What I can do, just to sort of make sure you have everything, is send it off to the list. So what I'll do here, what's the best way to send this? I don't want to send it that way. Shall we try it with Blackboard? Oh, geez, he's going to make me log in again? That's just annoying.
It won't let me submit another.
Yeah, it's like once unlocked.
Oh, really? That must be some sort of a thing that I can change. There's somebody here who said to me that I could create a forum. Create forum, and what we'll do is we'll call this the Hurst forum, and you guys can all email to each other with the Hurst forum, and I'll just say here is some random motion. I'll call it rectified, I don't know, random white noise walk. It's the random white noise walk. That sounds like a dance step. And it's got a little bit of stuff in there for you to look at and try if you want to. Available, no restrictions, standard view, no grading, allow members to subscribe, allow posts. Is there anything here I need to... so many options. I'm still learning. Submit. Now, do you get this in an email? I don't even know. It just got posted as in a discussion, so you don't even see it in an email? See, if I posted it to the Yahoo group, it would be in an email and it would be retained.
Yeah, do you see the 74 on the top right?
Yeah, what's that?
That's like notifications.
Yeah, we'll get that. No, like something that was posted.
Yeah. You just send emails.
Where's this? There's due dates, posts, updates, retention, calendar.
That would be if you send us all the email. You have to like do something.
You
It just automatically go. Yeah, you can do like send email to the whole class.
Oh, over here.
Yeah.
Yeah, but then it doesn't retain it. I mean, I can certainly send it to all users, but then it's only in your inbox. The Hurst code, right? And now it's not there.
Is there a way to do like an announcement?
Well, I guess you're all going to get it now, because I sent it to you. Right?
Yep.
So
Some professors, they do like an announcement, it'll show up on there, but it also is
I like the email.
I think the email's better because you're getting it on your inbox and you can cut and paste it into whatever.
yeah, I thought there was a way to do both.
If I was in a Yahoo group, I would send it to the group and then it would be retained as documentation for, let's say, the next class, which I would like. And also it makes it searchable. But then anyone can see it. But that's alright with me, I don't care. Okay guys, that's what I got for today. You've got a homework assignment. I hope it's not as challenging as the last one.